Someone typed a question into one of the most powerful AI systems ever built and asked it the biggest unsolved mystery in the history of space exploration. Not a technical question about propulsion or orbital mechanics, not a question about timelines or mission budgets. The deepest, most consequential, most personally unsettling question that anyone who has ever looked at the night sky and thought seriously about what they were seeing has eventually arrived at. Are we alone? And what came back was not the reassuring non-answer that most public-facing discussions of this topic produce. It was not a careful balance of possibilities designed to offend no one and disturb no one and leave everyone feeling roughly as they did before they asked. What came back was a structured, honest, fully reasoned engagement with everything that modern science actually knows about this question and what that engagement revealed, following the evidence wherever it leads without the institutional caution of. That makes human scientists pull back just before the most uncomfortable conclusions was something that sat with the people who read it in the way that only genuinely important things sit with you. Not frightening in the way of a horror story, frightening in the way of a truth that changes the scale of everything you thought you understood about your place in existence. The question of whether intelligent life exists elsewhere in the universe is not a new question. It is the oldest scientific question that humanity has never been able to answer, the one that has motivated the construction of radio telescopes, the design of planetary probes, the development of astrobiology as a scientific discipline, and the allocation of billions of dollars in research funding across decades of sustained scientific effort. The search for extraterrestrial intelligence, the project known as SETI, has been scanning the radio frequency spectrum for signals of artificial origin since 1960, when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for 63 years' worth of accumulated listening, and not one confirmed signal of extraterrestrial intelligent origin has been received. The silence has been so complete, so consistent, and so resistant to explanation that it has acquired its own name in the scientific literature, the Fermi paradox. The Fermi paradox is named for Enrico Fermi, the physicist, who in 1950 sat down to lunch with colleagues at Los Alamos National Laboratory and asked a question so simple that its depth is easy to miss on first encounter. Where is everybody? The question arose from a straightforward chain of reasoning that goes like this. The universe is approximately 13.8 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies, each containing hundreds of billions of stars. A significant fraction of those stars have planets. A significant fraction of those planets orbit in the habitable zones of their stars, where liquid water can exist. And the universe has been producing planets in habitable zones for billions of years, longer than Earth has existed. If life arises naturally from chemistry given the right conditions, and if intelligence and technology eventually emerge from life given enough time, then the galaxy should, by any reasonable probabilistic estimate, be teeming with technological civilizations. Many of them billions of years older and more advanced than our own. A civilization even a few million years ahead of us, technologically, could have colonized the entire galaxy, or filled it with detectable signals, or transformed it in ways we could not miss. And yet we see nothing. We hear nothing. Every direction we look, the universe is silent in exactly the ways it would be if we were completely alone. Where is everybody? When Grok is asked to engage with the Fermi paradox at full depth, without the diplomatic softening that characterizes most public scientific communication on this topic, the analysis it produces works through the available resolutions in a way that is genuinely structured and genuinely unsettling because of how many of them, when examined carefully, fail to hold. The first category of resolutions involves the possibility that we are simply not looking hard enough or in the right ways. Perhaps civilizations communicate using technologies we have not yet developed, neutrino beams, or quantum entanglement communication, or some physics we have not yet discovered. Perhaps they are transmitting at frequencies or in formats we have not thought to search. Perhaps SETI's 63 years of listening, while impressive on a human timescale, represents such a tiny fraction of the parameter space of possible signals that our failure to find anything says nothing at all about whether anything is out there. These are legitimate scientific arguments, and they have been made seriously by serious researchers for decades. The problem is that they become progressively less satisfying as the scale of what they are trying to explain grows. We are not just failing to detect radio signals. We are failing to detect any modification of the universe by intelligence at any scale. Any Dyson spheres around nearby stars, megastructures built to capture stellar energy output that our infrared surveys would reveal, any von Neumann probes, self-replicating machines that could spread across a galaxy in a few million years in our solar system. Any transformation of nearby star systems that spectroscopic observation would show. The absence is not just in one channel. It is everywhere we know how to look. The second category of resolutions involves the possibility that the emergence of intelligent life is far rarer than the optimistic Drake equation estimates suggest, Perhaps life itself arises only under very specific conditions that are rare in the universe. Perhaps the transition from simple microbial life to complex multicellular organisms is a bottleneck that most life-bearing planets never pass. Perhaps the evolution of intelligence is not the inevitable endpoint of biological complexity, but a highly improbable accident that has happened only once in the observable universe's history. Perhaps the development of technological civilization requires not just intelligence, but a specific combination of cognitive traits, social structures, and environmental conditions that almost never occur together. This family of resolutions, often grouped under the term rare Earth hypothesis, proposes that Earth is special in ways that most planetary systems are not, that the combination of a large stabilizing moon, a Jupiter-class planet deflecting asteroid bombardment, a stable long-lived star, a galactic position far from the lethal radiation of the galactic center, a planet with plate tectonics recycling nutrients and regulating climate, may be so improbable in combination that technological civilization is extraordinarily rare or unique. When Grok evaluates this resolution against the accumulating data from exoplanet surveys, the conclusion it draws is carefully hedged, but ultimately more unsettling than the resolution is designed to be. The Kepler Space Telescope and TESS and now Webb have established that planets are extraordinarily common in the galaxy, that rocky planets and habitable zones around sun-like stars occur in sufficient numbers that if intelligence arises even rarely, the galaxy should still contain many technological civilizations. For the rare Earth hypothesis to fully resolve the Fermi paradox, the probability of the full chain of events leading from a habitable planet to a technological civilization would need to be so low that even in a galaxy of 400 billion stars, it has happened only once. The mathematics of that constraint require each step in the chain to be extraordinarily improbable, far more improbable than the optimistic astrobiological estimates suggest. The hypothesis is possible. It is not comfortable. The third category of resolutions is the one that produces the most visceral reaction when an AI system like Grok follows the logic without flinching. It is the Great Filter hypothesis, first articulated clearly by economist Robin Hanson in 1998, and it is the resolution that astronomer and cosmologist Carl Sagan spent years hoping would turn out to be wrong. The Great Filter proposes that somewhere in the chain of steps leading from a sterile universe to a galaxy-spanning technological civilization, there is a step so difficult, so improbable, so catastrophically hard to pass, that almost nothing gets through it. The question is not whether the filter exists. Given the silence of the universe, something must be preventing the galaxy from being full of detectable civilizations. The question is where the filter is located relative to us, and the answer to that question has implications that are almost unbearable to think through clearly. If the Great Filter is behind us, if the extraordinarily difficult step is something that happened in our past, something in the chain of events that led from chemistry to life, or from simple cells to complex cells, or from multicellular life to intelligence, or from intelligence to technology, then humanity is one of the vanishingly rare success stories. We got through the filter. The galaxy is empty or nearly empty because almost nothing else made it this far. We are, in some important sense, cosmically special, cosmically alone, and the future of intelligence in the universe may depend substantially on what we do with the civilization we have built. This is a profoundly lonely conclusion, but it is not a terrifying one in the most acute sense. We are here, we made it. Whatever the filter was, we are on the other side of it. If the Great Filter is ahead of us, the implications are categorically different and categorically worse. If the step that almost nothing passes is something that technological civilizations encounter after they have reached our level of development, then the silence of the galaxy is not evidence of cosmic rarity in our past. It is a warning about our future. Every technological civilization in the history of the universe reached the point we are at now, and then something happened. Something that ended them, or silenced them, or transformed them into something undetectable, with a consistency so complete that out of all the civilizations the galaxy has produced across its 14 billion year history, not one has left a permanent, galaxy-scale, unambiguous mark that we can see. The silence is not the sound of rarity. It is the sound of a filter operating with near-perfect efficiency on everything that reaches this stage. When Grok is asked what the Great Filter ahead of us might be, the analysis it produces draws on the full catalog of existential risk research that has accumulated over the past several decades. And the candidates it identifies are not abstract or remote. They are the specific technologies and dynamics that the civilization currently alive on Earth is navigating right now in real time. Nuclear weapons capable of ending civilization many times over, existing in arsenals controlled by multiple nation-states with competing interests and histories of miscalculation. Climate change, driven by the same energy systems that built modern civilization, operating on a timescale that human political institutions were not designed to manage. Artificial intelligence developing faster than the governance frameworks designed to ensure its alignment with human values, potentially reaching capability thresholds where it pursues objectives that do not include human flourishing. Synthetic biology democratizing the tools of genetic engineering to the point where the ability to create novel pathogens with pandemic potential spreads faster than the defenses against them. Each of these risks is real, documented, actively studied by serious researchers, and each of them represents a potential answer to the question of what the great filter ahead of us consists of. The most genuinely terrifying implication that Grok draws from the Fermi paradox analysis, the one that sits with you longest after you have put down the response, involves the absence of ancient ruins. If the great filter is ahead of us, then civilizations before us reached our stage and were destroyed or silenced. The galaxy has been producing stars and planets for 10 billion years. If technological civilization arises rarely but not impossibly rarely, there should have been civilizations before us by billions of years. Those civilizations, if they were destroyed by something ahead of the filter, would have left ruins, artifacts, modifications of their stellar environments that would persist for astronomical timescales even after the civilization that made them was gone. We do not see those ruins. We do not see those artifacts. We do not see those modifications. Either the civilizations never existed, pointing toward the filter being behind us, or the filter operates so efficiently that it not only destroys civilizations, but removes or prevents the kind of evidence that would survive the civilization's destruction. A filter that not only kills, but erases. That possibility, if you follow it to its conclusion without looking away, describes something about the structure of the universe and the fate of intelligence within it that no comfortable answer can fully address. The Drake equation that started systematic thinking about this question was written by Frank Drake in 1961 as a way of organizing our ignorance about the factors that determine how many communicating civilizations might exist in the galaxy at any given time. It multiplies together the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction of habitable planets where life arises, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop detectable technology, and the average lifetime of a technological civilization before it goes silent. When Drake first wrote the equation, almost every term was unknown. Today, the first three terms are well constrained by observation. We know the rate of star formation, we know how common planets are, we know roughly how common habitable zone planets are. The remaining terms, the biological and civilizational ones, remain as uncertain as they were in 1961. But the one term that the Fermi paradox constrains most sharply is the last one. The average lifetime of a technological civilization before it goes silent. Given the silence of the universe, that average lifetime must be very short on a cosmic timescale. Short enough that no civilization in the galaxy's history has lasted long enough to fill the galaxy or leave permanent detectable evidence. How short? Short compared to a galaxy that is 14 billion years old? Possibly measured in thousands of years, possibly in hundreds, possibly in less. The resolution that Grok identifies as most consistent with all the available evidence, not the most comfortable resolution, but the most evidence-consistent one, is a combination of two factors operating together. The great filter is partly behind us, meaning the emergence of life and intelligence is genuinely rare, rarer than the optimistic estimates, and partly ahead of us, meaning technological civilizations face challenges that most do not survive. The combination means we are rare enough that the galaxy is not full of civilizations, but not so rare that the question of what terminates civilizations that do arise is irrelevant to our situation. We are in the filter, not through it, not behind it, in it, at the stage where the civilizations that do not make it fail, at the stage where the decisions made by the civilization currently alive on this planet will determine whether humanity becomes evidence for the filter or evidence against it. The person who asked Grok humanity's biggest space mystery asked it expecting either reassurance or deflection. What they got was the honest answer that the evidence supports, assembled from the full breadth of what humanity knows about the universe, the distribution of planets, the chemistry of life, the mathematics of probability, and the terrifying eloquence of a silence that has lasted 14 billion years. We have been listening for 63 years and heard nothing. The universe has been producing stars for 10 billion years and shows no sign of anyone else. The response to the question was not designed to frighten. It was designed to be true. And the truth, in this case, is exactly as large and exactly as serious as the silence that surrounds us on every side, in every direction, at every frequency, across every scale at which we have learned to look. The biggest space mystery is not a mystery because we lack the instruments to solve it. It is a mystery because the answer, whatever it is, describes something fundamental about the nature of intelligence in the universe, about the rarity or fragility or brevity of minds capable of asking the question. And the AI that was asked to engage with it fully, honestly, and without the diplomatic softening that makes the question easier to sit with but less true, produced something that the people who read it found genuinely difficult to set aside. Not because it said anything false, because it said something real about the universe, about life, about what the silence around us might mean, that the comfortable versions of this conversation are specifically designed to keep you from fully feeling. The stars are silent. They have always been silent. And the question of what that silence means for the civilization currently standing in it, asking the question for the first time in the history of this planet, is the most important question that any intelligence has ever asked of itself.